Hello, so in this video we'll talk about a few more properties of sequences. To be specific, when do we say that a sequence is bounded? And what does it mean when we say that a sequence is monotonic? And we'll end this video with a nice theorem that will actually tell us something about the convergence of these types of sequences. And so, first thing I want to define is something you have seen it before in relation to functions, and it's an increasing or a decreasing sequence. And so a sequence is said to be increasing if, well, as the name suggests, succeeding terms are larger than the previous terms. Right? So if you're starting with A1, then A2 is strictly larger than A1. A3 is strictly larger than A2, and so on. Right? And note that it's not strictly larger or equal. Right? It's not less than or equal to signs here. It's just strict inequalities here for it to be increasing. For a sequence to be decreasing, it's basically the same thing, but now A1 is larger than A2, which is larger than A3. So succeeding terms, their values are smaller than terms that come before them. And well, monotonic, this term, is just a general term to describe any sequence that's either increasing or decreasing. And I want to note here that n is larger than or equal to 1. So this quantifier here says this relationship has to hold for all your terms in the sequence. Right? So you can't have a sequence where it starts off here, goes up, and then decreasing after n larger than or equal to 2. Right? So that's not a decreasing sequence, because at the very first step it went up. Right? So something is decreasing if it's decreasing everywhere. Something is increasing if it's increasing everywhere. Okay, and so a few examples here. How can you actually tell whether a sequence is increasing or decreasing? Look at n plus 1 over n. The n term here, clearly increasing, goes up, while the 1 over n term here is decreasing. So what would we do here? Well, one thing you can do at the beginning is start plugging in numbers and just see what we get. When n equals 1, that's 1 plus 1, which is 2. When n equals 2, that's 2 plus 1/2. When n equals 3, that's 3 and 1/3. 4 and 1/4 for n equals 4, and so on. And from here, you can actually make a guess that it looks like the sequence is increasing, right? How do I know that? If you look at all these terms, it's pretty much divided into an integer part and a fractional part, right? N is an integer, 1 over n is a fraction, right? Or a decimal. So what this tells me is, from term to term, the integer part always goes up by 1. And so really it doesn't matter what that fractional part is, right? That you have a fractional part that's decreasing. Overall, the sequence is still increasing. There's 2 point something, 3 point something, 4 point something, and so on. Right? So intuitively, you can determine it that way. But you can, remember, also prove it using calculus here. In fact, what if we define the function f of x to be x plus 1 over x? Well, then the derivative is 1 minus 1 over x squared. And what can we say about 1 minus 1 over x squared? Well, for any x value that's larger than 1, this is going to be larger than 0. Right? In fact, when x is equal to 1, it's exactly 0. And then when x equals, well, any number larger than 1, this is going to be strictly positive. So because of the fact that you have a function and your sequence lives on that function, if your function is increasing throughout, then the sequence is also increasing. Okay, so in this case, the answer is It's an increasing sequence. Okay, let's talk about boundedness now. We'll say that a sequence is bounded above if there's a number m such that a sub n is less than or equal to m for all n larger than or equal to 1. Okay, I just read that definition there. I just read that first sentence. What does that mean? It means we have a sequence. It doesn't matter if it's increasing or decreasing. We'll say it's bounded above if you can find some value, capital M, for which all the terms of your sequence are below that horizontal line. Bounded below is similar. It's bounded below if you can find the horizontal line here such that all the terms of your sequence are above that horizontal line. Right? Bounded below and bounded above. And if your sequence has both a capital M and a small m, so this is a typo here, it should be small m, that bounds it from above and bounds it from below, then we just say the sequence is bounded. Okay, so how can we tell that a sequence is bounded or unbounded? Well, usually you have to prove some inequalities. Let's see, like n over n plus 1. We already saw what that looks like. Right? That's 1/2, 2/3, 3/4, 4/5. And we know that it has limit 1. Right? It approaches 1 as n goes to infinity. But in fact, we don't even need to talk about the limit there. We can just say n over n plus 1 is always less than 1 for any n larger than or equal to 1. Right? Because that's a fraction where the top and the bottom are both positive and the top is smaller than the bottom. So a sub n is less than 1 for any n. Well, because of the fact that it's positive, we can also say a sub n is larger than 0 for any n in the natural numbers. Therefore, this is bounded. Okay. How about minus 2 to the n? Well, we already saw from last time that that's not a bounded sequence. Right? Because its terms alternate in between the two curves 2 to the n and negative 2 to the n. And both branches go to infinity, right? It just blows up to infinity. And you can argue it this way. It's that for any capital M I choose, say I choose this value, capital M, I can always take n large enough so that I get some point in my sequence that's above this horizontal line. Right? For example, if I told you that, hey, maybe 1,000 is an upper bound, well, clearly I can immediately say that that's not true because I can take n equals 6. No, not n equals 6. What am I saying? N equals 10, right? And picking n equals 10 is going to give me a sub n equals 1,024, which is above that horizontal line. So if for any capital M, I can do that, right? I can pick some number above that line, then it's not bounded above. Right? So it's the same thing for bounded below. You'll never find an upper bound or a lower bound. Okay, so it's neither bounded above nor bounded below. And finally, this theorem combines those two properties and actually concludes that if you know that a sequence is both bounded and monotonic, then it's convergent. Now, the idea behind this theorem is if you know that you have bounds on your sequence, and it's monotonic, right? So it's either increasing or decreasing throughout. So let's assume it's increasing for now. Then the terms of your sequence have to increase, but since it's bounded above, it's going to have nowhere to go, right? It's going to have to approach a limit. Now, the limit might not necessarily be whatever upper bound is that you found for your sequence, right? All this theorem says is that the limit exists as n goes to infinity. It doesn't tell you what that limit is. In fact, if you know that your sequence is increasing, you don't really need your lower bound, right? It's bounded from below by the first term, trivially. Right, so my first term could have been like here, for instance. That's a lower bound. So it doesn't really come into play. If your sequence is decreasing, then it's the lower bound that you might be approaching as n goes to infinity. Right? But again, it might not necessarily be L as well. Right? The limit may be something slightly larger than your lower bound. And yep, I mean, if you wanted to evaluate the limit, you're still going to have to rely on those limit laws, right, that we talked about before. Or maybe the squeeze theorem, right? L'Hopital's rule. But this is a nice theorem, regardless, right? It's an example of one of these things where, you know, just knowing some characteristics of our sequence actually gives us this very nice conclusion. And that is convergent.